In this week's lecture, I'm going to talk about user equilibrium with elastic demand. A little bit of background again from previous weeks. We've talked about transport planning, how travel demand and supply works. We talked about network representations, nodes, links, demand matrices. We talked about the definition and mathematical formulation of traffic assignment, the selection of the routes between origin and destinations, the concept of shortest path finding, Dijkstra algorithm, for example, the concept of convexity, constraint optimization algorithms, methods like golden section and bisection. We talked about user equilibrium a lot, a theory that tries to represent how people choose their routes in a network. Then we covered some solution methods for UE, such as MSA, Frank-Wolf, gradient projection method. And now it's the right time to actually talk about an extension of the UE problem that assumes elastic demand. What I will do this week is I will first start with some motivation and interpretation of elastic demand. What is elastic demand, and what is it that's trying to represent? Then I'll cover the mathematical formulation of it, and then we'll talk about some solution methods that can be applied to real problems. So the motivation behind user equilibrium extension with extension of user equilibrium to elastic demand situations is that we want to know, we want to understand how users actually react to traffic congestion. For example, if you're driving to work and if you see that your travel time is too long, what will happen? Users, again, it's the work it's work, right? You can't really suppress, you can't really give up the trip, right? So you can't really say, okay, I'm not going to go today. You can, or work from home these days, but classically, you wouldn't say I'm not going to work today, right? So users may actually switch to alternative modes. Instead of driving to work, you may say, okay, I'm going to take I'm going to take train, I'm going to take a bus, I'm going to bike to my work today. Or you may also adjust your departure time. Instead of saying, hey, it's congested today, and if I leave now, it's going to take an hour and a half to get to work. How about I leave maybe 15 minutes later, or maybe 15 minutes earlier? You switch your departure time to actually save on your travel time. So, and this behavior happens a lot, right? So whenever you want to go somewhere, you actually plan to not only avoid the congested routes, but you also avoid the congested times in the network, right? And again, this kind of behavior is representing what we call elastic demand. Elastic demand means travel demand in a network is not necessarily fixed. For example, if I have 10 people, in all previous examples that we've covered, we always had, we have 6 people going from O to D, from this origin to that destination, or 10 people, or 20 people, or 1,000 people going from this origin to destination. And that number was always fixed, right? But in reality, that number is not necessarily fixed every day. Some people decide to switch to another mode of travel. Some people decide to switch their departure time. So that demand actually could be mathematically formulated as a function of the travel time itself. If the shortest path travel time goes high, people may start switching, not switching routes, but I mean switching the travel mode or switching the departure time. When the shortest path travel time goes down, which is a desirable situation, we may see it that all of the demand are actually sticking to their original departure time, or sticking to their original transport mode that they decided to go with. But one assumption we have to make is that users know what is the minimum travel time between any OD pair. And we assume that this minimum travel time, of course, this minimum travel time is responsive to the flow on that path, right? It's like the travel time function. Two other points here is if the minimum travel time between any OD pair is as low as possible, a maximum number of users will travel. So that's the desired case, right? For each individual person, that my minimum travel time that I've experienced previously in my history of travels, if that minimum travel time today is as low as possible, I would say, yes, that's a low travel time, and I'm happy to stick to whatever plan I had before. I'm going to drive to work, or I'm going to stick to this departure time. So we're going to see, if not all, but the majority of the demand that wanted to travel will travel. But conversely, if the minimum travel time between any OD pair is significantly higher, for example, yesterday the minimum travel time was 10 minutes, but today, because there was an accident, there was a construction, the minimum travel time from what I see in my Google Maps, for example, it's going to be 40 minutes. Previously, it was 10 minutes. Today, it's going to be 40 minutes. So what's going to happen? Demand will go down. I say, hey, I'm not going to drive. That's going to take a long time to get to work. I'm going to take a train. I'm going to take a bus. I'm going to work from home. I want to switch my departure time. I don't want to leave now. It's too congested. I may just get to work 1 hour later, but I'm not going to waste my time in congestion, right? So if that minimum travel time is significantly higher, demand will go down. But how can we represent this behavior mathematically? We can define a small d subscript rs as the travel demand between origin destination pair RNS. So the small d represents the demand. KRS represents the minimum travel time between each OD pair, which is also equivalent to the dual variable in the Lagrangian function from the optimization slides that we've covered before. And what we can define is we can define something called elastic demand function. This capital D is a function which we call elastic demand function, which says that the demand that really travels in the network is a function of that minimum travel time. So DKRS. So that demand function can also be different for every OD. So that's why we put RS here. But if it was the same for every OD, we would just simply say DKRS. But let's take a general case that this demand function could be different for every OD. So we say function DRS, we may have as many demand functions as we have as OD pairs we have in the network. And we say it's a function of the minimum travel time. And I mean, we'll talk about this later a bit more, but we assume that this function is monotonically decreasing. I mean, the reason we assume this is because, again, if you remember from the optimization, and if you want to get unique link flows, what was the condition for the travel time function? The travel time function had to be monotonically increasing. So the objective function in the optimization of the UE was strictly convex, so we could get unique link flows, right? If we also still want to get unique link flows, and if we still want to have a convex objective function in our UE optimization, we need to assume this demand function is monotonically decreasing. Again, I'll talk about this a little bit more in a minute. So the demand function D can include OD-specific parameters. It can even include parameters such as population size, density, income distribution, vehicle ownership, number of jobs, etc., etc. But here in this course, just for the sake of simplicity, we only assume that the demand function is only a function of the minimum travel time KRS. So our demand function would only look like something like this, like 50 plus KRS or minus KRS, or KRS multiplied by 2 plus something. So it will only have KRS in it. But in reality, it may have a lot more parameters in it, a lot more variables in it, trying to represent how the ODs look like in terms of land use, population and demographic and job distribution. But here, it's going to be only a function of travel time. So let's have a look at an example and see how this concept of elastic demand come into play. So consider the following small network with 2 links and 1 origin destination RS. The travel time functions on each links are given, and this is going to be our demand function. You see, the demand is no longer fixed here. Rather, it's a function of this minimum travel time. Minimum travel time. 60 minus KRS. So this is our elastic demand function, and we have this linear travel time functions. So if we want to go after UE, and if both passes are used, if we wanted to solve this algebraically, what should we do? We put together some simultaneous equations, right? So we would have said if both paths are used, the travel times on both passes must be equal. So this is that the travel time on path 1 must be equal to the travel time on path 2. And then we also have a demand conservation equation, right? Which says x1 plus x2, the number of flows coming out of origin going into 2 different paths, x1 plus x2. x1 plus x2 must be equal to demand, right? But here demand is no longer fixed, so I can't just put a fixed constant number here. I would say x1 plus x2 is actually equal to 60 minus KRS. I put my demand function here instead of a fixed demand, okay? But we have 3 unknowns here, right? So we have x1, x2, and KRS are all unknown, and I only have 2 equations. So I need to actually come up with another equation to be able to algebraically solve this, right? So what should be the third equation that we can put together to simultaneously solve this system of equations? Remember, we said this KRS is actually the minimum travel time. So what does it mean? Minimum travel time. That actually means at the equilibrium, whatever the minimum travel time is, it is equal to that KRS. So at the equilibrium, we said this is T1, this is T2, and T1 is equal to T2. And this KRS was actually defined as minimum travel time, right? And again, going back to the optimality conditions of our Lagrangian function, this was also representing the shortest path travel time. And at the equilibrium, what is the shortest path travel time? It's actually T1 equal to T2, right? So we would have this new equation that KRS at the equilibrium is actually equal to T1 equal to T2. So I now have a new equation that I can use, that KRS, either you can go with KRS equal to T1 or KRS equal to T2, okay? So that's what I said here. So KRS is equal to T1 and it is also equal to T2. So now I have this new additional equation that I can put into my system. And then I have 3 equations, 3 unknowns, and I can algebraically solve it. And let's see how, again, if you algebraically solve this, you get to this solution. The link flow on the first link would be 20. You'll have 10 for the second link flow, and your KRS, the minimum travel time in the network, would be actually to, so KRS would be actually to equal to T1 equal to T2. KRS would be equal to T1 would be equal to T2, and it would be equal to 30, whatever that unit of time is. So what would be the demand? The actual demand that is using the network would be 60 minus KRS 30 is actually 30. So we see that only 30 people are actually using the network given the travel time conditions in the network. Okay, so it's an easy example where we algebraically solve UE given this elastic demand function. So But now let's do another little experiment here. Let's try to increase the travel time on one of the paths and see how demand changes, how demand responses to that travel time change. Are we going to see higher demand or lower demand? So what I'm going to do here is I'm going to make the travel time function of link 1 a little bit steeper. So look, previously it was 10 plus x1, right? Let me just check. Yes, it was 10 plus x1. And now I'm going to make it to 10 plus 2x1, so 2 times x1. So now this travel time functions is slightly steeper than the previous travel time. And now it would be interesting to see how this change in the travel time function actually changes the demand that really uses the network. Because again, we don't have a fixed demand. The demand function still remains the same as before, but what we end up finding at the equilibrium point is a different demand. So let's put together the simultaneous equations and solve this problem algebraically. So we have the demand conservation equation where we have the demand function is actually equal to x1 plus x2. We have the T1 equal to T2. So this is T1 equal to T2. And the last equation is actually the shortest path, or the minimum travel time is actually equal to either T1 or T2, right? So here I'm going with T1. So it's KRS is actually equal to T1. And if you put these equations together and try to solve it, I leave that to you. It's an easy system of equations to solve. You'll get link volumes 12 for link 1, you get the volume of 14 for link 2, and look at the demand. Look at the KRS, we get 34. So this is the shortest, this is T1 equal to T2 equal to KRS is 34. And what would be the demand? The demand would be 60 minus this 34, because that's the function, right? And that would give us what? 16. What was the previous demand? The previous demand was 30. Interesting. You see? What happened was by changing that travel time function on one of the links, we make it a little bit steeper, meaning that that link is more sensitive now to any increase in flow, because and it will result in higher travel times, and therefore the demand will go down because people will start either switching to other modes or start changing their departure time, or maybe just working from home. I'm not going to travel today. So because of that change in the travel time function, we see that demand will go down. And that is a nice, interesting, a nice example of how really elastic demand works, because it's no longer fixed. I think there's a question in the chat box. If I come back to it, just give me a second. Oh, sorry, 26. Yep. Oh, gosh. Yes. Apologies. Yes, 26. You know, there's an interesting function called, I don't know what it is called, but it is this, that if x-axis is your university degree progression, university, or actually education level. If this is your education level and y-axis is your simple math skills, it goes down. So when you're a kid, you start growing your skills in simple math, summing and subtracting, stuff like that, right? So it grows, it becomes good. As soon as you start your university degree, and if you continue your bachelor, your master, your PhD, it goes down. You become more proficient in some advanced mathematics, taking fancy derivatives or taking complicated integrals, doing all this convex optimization stuff, Lagrangian function with multiplier. But then when it comes to subtracting 60 minus 34, you get it wrong. So that's something we always observe. But anyways, yeah, I think there was another question or maybe a laugh in the chat box if I come back to it. Yes. Okay, let me continue. I think I talked about the interpretation. So originally it was 30 people traveling, then it reduced down, it reduced to 26 people because of that behavior that we mathematically represented here. So hopefully with this example, you have a better understanding of how elastic demand works. But now another question comes up. Sure, this is the algebraic way of solving it. But how can we put together a new formulation for the UE travel assignment, traffic assignment, that incorporate this elastic demand? What time is it? I think we still have time. So let me go through this. And then, yeah, maybe, yeah, I think we still have, it's too early for a break, right? So let's keep going, and then maybe we can even, if we can even finish the class early today. But let me continue because it's too early, I guess. So here, I'm going to talk about the formulation of the UE with elastic demand. So let's revisit the formulation of the UE with fixed demand case, as we talked about before many times. So the objective function was we want to minimize the summation of the area underneath the travel time functions for every link. So this integral was what? If this is my link travel time function, it is actually the area underneath each link travel time. And then if we sum it across all the links in the network, right? Sum over all links in the network. So that was the Beckman function, and then that's the minimization. And then we had the non-negativity constraint, we had the demand conservation constraint, and we had the relationship between path flows and link flows. In this case, demand was fixed, obviously. You can see here, DRS, this demand is fixed. But now, if we want to include elastic demand into the UE, what we can do is we can actually add an additional term into the objective function. So we add this new term into the objective function, which says we want to minimize this Beckman function minus the summation across what? The summation over all ODs this time. Summation over, so this is the summation over all ODs of what? The integral, or basically the area underneath the inverse of the demand function. So again, if this is my demand function, if this is my demand function, something like this, look, the demand function must be monotonically decreasing, but the inverse of it will be increasing, right? From 0 to DRS. So this is my X as well, and this is my demand. So this area underneath the demand function, the inverse of the demand function, so this is D minus 1. The area underneath the demand function, if we take the integral of that for every OD, look, the demand function, look, the travel time function previously was an attribute of the link. This demand function is attribute of the ODs, okay? It's not an attribute of the link. It's an attribute of the OD. So that's why we're summing across all the ODs. So we take that integral, and then that would be an additional term into the objective function. And let's have a look at the constraint, and let's see how they're changed. We still have this relationship that relates path flows and link flows. we have this, whatever the demand is at the end, the summation of the path flows must be equal to that demand, right? So this demand is no longer fixed, but it is a function of this dkrs as we talked about. But whatever that demand is at the end, this should be equal to the demand, right? We want to converse, we want to have demand conservation, but the demand is no longer fixed. And we have this, yes, non-negativity constraint for the flows, and we have this new constraint here that the demand should also be non-negative, right? Because it doesn't mean to have a negative demand. So that would be the new formulation of the UE with elastic demand. So we just add a new term into the objective function, and we add this new constraint into the set of constraints. So now let's actually consider the same network as we saw before, and let's try to write down the objective function for the UE here. So we had the demand function, we have the link travel time functions, and we need the inverse, right? So if I go back to the objective function, so in the objective function, we need to have the inverse of the demand function, right? So let's take the inverse of this function. If I want to take the inverse of this function, what I need to do, if you remember by how to inverse a function, again, relating to that graph that I said, the more you do university degrees, your simple math skills go down. So we just need to take this KRS out and put D inside it, right? So D minus 1 would actually be equal to KRS, and that would be equal to, yeah, let's call this D. Let's call this DR, small DRS, because that's what we have in the UE formula. So then it would be 60 minus DRS. So my inverse function is actually 60 minus DRS, right? So that would be my inverse of the demand function. And again, if I go back here to the objective function, so that's the inverse function of here. And again, let me just add another comment here. This DRS here, you see how I said DRS, just to take that inverse function, we said DRS is actually equal to DRS KRS. So instead of this DRS, a small DRS, I could actually just replace it with that capital DRS, the actual function, right? It's just, they're just equivalent. That a small DRS, the demand is equal to that demand function, right? So anyways, so we take the inverse of the demand function, and that would be my inverse of the demand function. And now let's put all of this into the UE objective function. So we want to minimize the summation of the integral of the travel times over all links minus, so this would be the summation of the integral of the link travel times across all links. Here we only have 2 links, minus the integral of the inverse of the demand function from 0 to D. Okay? And then what are the constraints? Here is a very easy example. So link x1 is actually equal to path flow 1, because this is only a path. So this is one path that contains only one link. So path flow is equal to link flow in this case, right? So x1 is actually equal to f1. Here is x2 is actually equal to f2 as well, right? This is path flow, and this is link flow. So because it's a path with one link, so of course path flows and link flows are going to be equal. But this is basically representing that relationship between path flow and link flow. And then I have this demand conservation constraint, and I have the non-negativity constraints for all my path flows and my demand as well. So this is how I have put together, this is how you should put together the UE formulation in an optimization context with elastic demand. But now let's try to derive the optimality conditions for it, where it gets a little bit more mathematical. Remember, we had to take the Lagrange, we had to put together the Lagrangian function, taking some derivations with the Lagrangian function with respect to the multiplier and the each link each link flow, and then we would come up with a set of optimality conditions. So I don't want to repeat myself. We can refer back to that optimality conditions of the UE with fixed demand, and then we're going to build on that here today. So what would be, so the first thing to do is let's simplify the objective function a little bit. So we had the original Beckman function term in it, and we added this inverse demand function here. So how about we call the first one Z1 and the other one Z2? So Z1 is the minimization of the integral of the link travel times, and Z2 is the minimization of the integral of the inverse of the demand function. So we can just write it as Z1 minus Z2 here. But look, there's an interesting difference here. Z1 is a function of what? This is link flow itself as a function of pass flows, right? How about the second term? The second term, Z, is actually a function of demand. And as I said before, this is summation across all links. This is summation over all links because travel time is an attribute of a link, while this term is actually summation over all ODs because that demand function is an attribute of or a property of the OD, not links. So now let's put together the Lagrangian function. So the Lagrangian function, again, it looks exactly the same as before. We have the objective function here, and we bring the constraint into the Lagrangian function, if you remember. This was the demand conservation, right? So we bring the, as we did before, we bring the constraint into the objective function, and then we introduce this multiplier. Right? So this isn't new, and nothing here is new except this additional term into the Lagrangian function. And again, because now we have a new variable in the Lagrangian function. Previously, the Lagrangian function was a function of pass flows and that dual variable. Now, if you look, the Lagrangian function is a function of the path flows, demand, and that multiplier that we had. Okay. And now, if we want to take the optimality conditions, it's just an extension of what we had before, which we took the derivative of the Lagrangian function with respect to path flows. We took the derivative of the Lagrangian function with respect to the multiplier. And now, because we have a new variable into the Lagrangian function, we take the derivative of the Lagrangian function with respect to demand. So this is new. We also had this before, that we take the derivative partial differential of the Lagrangian function with respect to pass flows multiplied by the pass flows, and that must be equal to 0, right? We had this before, so this is not new. But an additional term that is new is also this one, which we say very similar to what happened with pass flows, because we now have a new additional term in the Lagrangian function. We say taking the partial differential of the Lagrangian function with respect to demand multiplied by demand should also be equal to 0. Very similar to this one, but instead of taking the derivative with respect to f, we're taking the derivative with respect to d. Okay, so the only two new conditions that are added to the set of optimality conditions are these two, and also this one. Did I have this one? No, yeah, this one. Demand must be non-negative. This is also new. So we had 3 actually. So the non-negativity condition for the demand as well. But now, I think the difficult part is actually taking those derivatives, right? So let me go over some of the fundamentals of how we can actually take that derivative of the Lagrangian function here. So if you remember from before, so this is from before. So in that objective function, we wanted to take this, in that Lagrangian function, we wanted to take the derivative of the Lagrange function with respect to pass flows. And again, I'm not going to repeat this. We had it before. And if you take that derivative, refer to my previous slides, we end up with this, that the cost of path K for any or D minus the KRS, the dual variable in the Lagrangian function. And if you want to make it equal to 0 or greater or smaller than 0, that's how we do it. And this KRS was the shortest path, if you remember, right? Shortest path, just SP, let's call it. So this is not new, we had it before, but now let's see, let's look at taking the differentiating L with respect to demand. That's the new differentiation that we have to learn how to take. So if you want to take that, if you go back to the Lagrangian function, if you want to take the derivative with respect to demand, we only need to keep those terms that have demand in them, right? So the first term in the Lagrangian function does not have any demand in it, right? So we can cross it out, because if you want to take the derivative with respect to demand, that would just come out as 0. The other two terms have demand in them, so we need to take the derivative of those if we want to derive this. So we say we take the derivative partial differential of this two terms. So this is this is my Z2, and this was the constraint that I had before, right? The constraint and the other term of the in the Lagrangian function. And again, it's not a difficult derivative to take here, because you can see that we have the integral of the inverse of a function, and if you want to take the derivative of that, this will just come out. So this will just come out, and we have a negative sign here, so we just put it there. And this term, the derivative is also easy. FRS is not dependent on demand, so we only have this part, and it's just KRS plus DRS. So if you want to take the derivative of that with respect to D, KRS only comes out. So we have KRS here. So the new differentiation will lead to this D minus 1 plus KRS. So that would be this new term that we need in the optimality conditions. And again, if we put all of the optimality conditions after taking the derivatives, this is the new set of optimality conditions. So this is from before, this is from before. This would be the new optimality condition, that demand multiplied by KRS minus D minus 1. Again, yeah, sorry. I had a frozen page again. Yes. So this is new. Sorry, let me just erase this check here and says this is new. We also have this KRS minus the inverse of the demand function must be non-negative. This is new. We had that from before. We had this from before, and the non-negativity of the demand is also new. So yeah, so this would be the new optimality conditions. And now, if we want to apply this optimization framework to a large scale network. Look, again, remember, why did we need all of this? Because in a large scale network, we can no longer apply algebraic solution, right? We can't really set up thousands unknowns and thousands simultaneous equations. We need another way. We need a smarter way to do it. And if we find link flows that satisfy these optimality conditions, that would be the UE solution with elastic demand. So let me see, what time is it? Let me continue with this example. Let me see what else I have here, because this isn't difficult. And then I stop when I get to this uniqueness, okay? This is the continuation of the optimality conditions. And when my son came in, that was a little bit of a break. So we used that a little bit, but I'm gonna give you lunch breaks. Don't worry, in like maybe 5-10 minutes. I'm hungry myself. So let's have a look at the same example as we had before. Where we had this easy demand function, we had link travel time function, and a small network. Sorry. I put together the objective functions for the optimization, minimization of summation of the link travel time function, integral of the link travel time functions across two links, minus the integral of the inverse of the demand function, subject to demand conservation, link flow path flows, and the non-negativity constraints, right? And now let's actually try to write the Lagrangian function for this example. So the Lagrangian function was what? The Lagrangian function, if I want to write it down here again, it was what? Lagrangian function as a function of f, d, and k was z1 minus z2 plus that k multiplied by the constraint that we had, right? So it would look like this, that we have the z1. So this is my z1, right? This is my z1 minus z2 plus the demand conservation constraint that is brought over into the Lagrangian function. So multiplier, and because there is only one, because there's only one OD here, I don't really have any summation behind this integral because it's only one OD, and I don't really have, yeah, that's same thing with here. I only have one OD, so there's only one multiplier here. Otherwise, for every OD, I should have had this new this I would have had more than one of these terms in my Lagrangian function. And then if you want to take, let's take the derivative of this Lagrange function with respect to f1 first, because we have two path flows, right? So if we take the derivative of the Lagrange function with respect to f1, what will happen is this one doesn't have f1, this one doesn't have f1. So the only two terms that have f1 is this one and the last term. And we'll have t1 x1 multiplied by the derivative of x with respect to f minus, if you look at here, f will just get out and we only have k coming out. So it would be minus k. So the derivative of the Lagrange function with respect to path flow 1 would simply be the travel time function at the travel time minus k. Similarly, if we can do the same thing for the second pass flow, it would exactly look like the same thing. The only difference is now this term is out. We only have this term and this term that they have f2 in them. So if you take the derivative of that with respect to f2, it would be just t2 minus k. And then we also need to take the derivative of the Lagrangian function with respect to demand, which this is out, this is out. These two terms we need to worry about. So derivative of this term would only be just minus the inverse of the demand function plus k, right? So not a complicated derivation. It's a relatively simple derivation here, right? So we take all of that. And then if I go back to the optimality conditions, look, we have the, this one, if I come back to this slide, yes. So we now have all the derivations that we need. We have the derivation with respect to f, we have the derivation with respect to d, we have the derivation with respect to k, and then if you just put together these optimality conditions and then find the link flows that satisfies all of these conditions, that would give us the UE solution with elastic demand in this example. But again, we're going to have a real numerical example soon, okay? So don't worry about seeing a real example. We're going to move from some of these mathematical optimization practices that we're doing now into real case, maybe in the second part of the lecture.